Welcome to today's paper reading. Today's paper is titled, Faithful Logical Reasoning via Symbolic Chain-of-Thought. This paper was published on the AR14 preprint by Jundong Su and colleagues from the National University of Singapore. The chain-of-thought (CoT) technique, while enhancing the reasoning ability of large language models, LLMs, faces challenges in handling logical reasoning that heavily relies on symbolic expressions and rigid deducing rules. To address this, the authors propose a novel framework called Symbolic Chain-of-Thought, SymbCoT. This framework integrates symbolic expressions and logic rules with CoT prompting. SymbCoT first translates natural language context into a symbolic format, then derives a step-by-step plan using symbolic logical rules, and finally includes a verifier to check the translation and reasoning chain. Evaluations on 5 standard datasets, involving both first-order logic and constraint optimization symbolic expressions, consistently show significant improvements over the CoT method and set new state-of-the-art performances. This system also demonstrates advancements in more faithful, flexible, and explainable logical reasoning. To the author's knowledge, this is the first work to combine symbolic expressions and rules into CoT for logical reasoning with LLMs. The pursuit of human-like logical reasoning is essential for achieving artificial general intelligence, AGI. AGI systems need to excel in problem-solving, decision-making, and critical thinking. Recent advancements in large language models, LLMs, have shown significant promise in semantic understanding, which is a step towards AGI. Enhancing LLMs to achieve human-level reasoning, especially in logical reasoning, is crucial. Logical reasoning is a fundamental form of reasoning that involves rigorous evidence evaluation and logical deduction. The latest trend is integrating LLMs with symbolic solvers to enhance their performance. However, these efforts have been limited to using LLMs as text-to-symbolic translators, with the core reasoning still relying on traditional external reasoners. This approach does not intrinsically strengthen LLMs' capability in logical reasoning and often results in inflexibility and unexplainability. To address these challenges, we introduce a novel symbolic chain of thought, SymbCoT, for logical reasoning. Unlike existing state-of-the-art LLM-based symbolic reasoning systems, SymbCoT is entirely facilitated by LLMs without relying on any external reasoners/tools. SymbCoT comprises 4 main modules: translator, planner, solver, and verifier. Figure 1 illustrates the difference between traditional chain of thought, CoT, and the proposed symbolic chain of thought, SymbCoT, in logical reasoning. It highlights how SymbCoT, using first-order logic, FOL, symbolic representations, provides a more precise and rigorous approach to logical reasoning compared to CoT's natural language rationales. This precision is crucial for problems requiring strict logical representation and clear inference rules. Figure 2 illustrates the workflow of our proposed symbolic CoT, SymbCoT, framework for logical reasoning. The framework consists of 4 main modules: translator, planner, solver, and verifier. The translator converts natural language premises and questions into symbolic format. The planner breaks down the problem into smaller subproblems, creating a step-by-step plan. The solver derives the answer through sequential logical inference, adhering to symbolic inference rules. The verifier validates the correctness of translations and the logical soundness of the reasoning process. SymbCoT integrates symbolic expressions with natural language to leverage the strengths of both, ensuring precise logical calculations and comprehensive interpretation of implicit information. The plan-then-solve architecture enhances the structure and trackability of the reasoning process, while the retrospective verification mechanism ensures the accuracy and reliability of the operations. Recent advancements in reasoning research powered by large language models, LLMs, have demonstrated significant progress, particularly in achieving human-level reasoning capabilities due to their deep semantic understanding. The chain-of-thought (CoT) series methodology has gained attention for its emulation of human discrete chain reasoning, enhancing performance in various applications. More advanced reasoning frameworks have been introduced, incorporating mechanisms like self-consistency and nonlinear topological structures, such as tree of thought and graph of thought. However, limitations in COT have been identified, particularly its reliance on natural language rationales, which can be disadvantageous in certain scenarios. Representing intermediate steps in a structured manner has been shown to improve reasoning capabilities for specific tasks. This paper proposes a symbolic-oriented COT approach tailored for logical reasoning, addressing the limitations of previous methods. The task of logical reasoning involves a set of premises P, which are logical statements, and the goal is to derive a conclusion about a given statement S. The conclusion can be true, false, or unknown based on the inferences drawn from the premises. For example, given the premises a hawk never lands and some birds are hawks, the statement all birds land is determined to be false. The SymbCoT system consists of 4 modules: translator, planner, solver, and verifier. The translator converts natural language premises and statements into a symbolic format suitable for logical analysis. The planner breaks down the problem into smaller subproblems, creating a step-by-step plan. The solver then uses this plan to derive the answer through a sequential logical inference process, ensuring each step is grounded in established logical frameworks. The reasoning process involves several steps: translating natural language into symbolic format, deriving a plan based on this symbolic context, and solving the problem using logical rules. For instance, the system translates premises like if a cartoon character is yellow, it is from The Simpsons into symbolic logic, and then uses this to solve the problem. Table 1 presents the performance metrics of various models on symbolic reasoning tasks using first-order logical representation. The GPT-4 model with SymbCoT strategy achieves the highest scores, significantly outperforming other methods. On GPT 3.5, SymbCoT also shows substantial improvements over naive, COT, and logic LM baselines. However, the Folio dataset presents a challenge for nonlinear reasoning, indicating areas for further model enhancement. Table 2 presents the results of GPT-4 on symbolic reasoning tasks using constraint optimization (CO) representation. The data shows that GPT-4 significantly outperforms both chain-of-thought (COT) and logic LM baselines. Specifically, GPT-4 achieves a 13.32% improvement over COT and a 3.12% improvement over logic LM. These results highlight the model's versatility and effectiveness in handling different symbolic reasoning expressions, particularly in complex reasoning tasks. In this section, the authors evaluate their method using GPT 3.5 and GPT-4 models, ensuring a fair comparison by using identical model parameters. They employ 5 standard datasets for evaluation, focusing on accuracy as the primary metric. The datasets include different symbolic structures, each presenting unique challenges in logical reasoning. The authors compare their method with a range of established baselines, noting significant performance gains across most datasets. However, they also identify challenges in nonlinear reasoning, particularly with the Folio dataset on GPT 3.5. Figure 3 presents the results of an ablation study on the GPT-4 model, focusing on the impact of removing different modules. The study reveals that the planner and solver components significantly enhance performance by an average of 10.4%, making them the most influential modules. The translator module also contributes to a secondary improvement of 6.3%. This highlights the effectiveness of the proposed plan-then-solve design, which breaks down complex questions into manageable parts, and the use of symbolic representation and rules for enhanced reasoning. Figure 4 illustrates the impact of reasoning depth on GPT-4's performance with the Proofwriter dataset. The red dual-head arrow visually represents the significant improvements our approach achieves over the vanilla chain-of-thought (COT) method. As reasoning depth increases, our method's advantage becomes more pronounced, highlighting its effectiveness in handling more complex reasoning tasks. Figure 5 compares the execution rates of our fully LLM-based reasoner against logic LM, focusing on the success rate of executing symbolic expression syntax. Our method achieves a remarkable execution success rate of up to 100%, representing a significant improvement over logic LM by an average of 17.7 percentage points. On the ARL-SAT, Our approach boosts the success rate by 67.4% from Logic LM, showcasing remarkable robustness against syntax errors. Figure 6 provides a detailed breakdown of the error types encountered by an external solver, categorizing them into information loss, IL, information error, IE, and others. The left pie chart illustrates the proportion of these errors, with IL and IE accounting for a significant portion. The bar chart on the right demonstrates the false rate attributed to IL and IE, which totals 100%. Additionally, it highlights the substantial reduction in false rates achieved through the implementation of our method, showing a 73.3% decrease in errors. In the analysis of complex reasoning, our approach shows significant improvement over the chain-of-thought (COT) method, especially in problems with greater reasoning depth. Even at a depth of 5, our method maintains the best performance, indicating its strength in handling challenging issues. Regarding robustness to symbolic syntax errors, our fully LLM-based reasoner achieves a 100% execution success rate, a 67.4% increase on the ARL-SAT, and a 17.7% improvement over Logic LM. This highlights our method's resilience against syntax errors. The hybrid expression of symbolic and natural language significantly reduces errors by 73.3%, with notable declines in information loss, IL, by 53.8% and information error, IE, by 19.5%, demonstrating the effectiveness of our approach in enhancing logical reasoning. Figure 7 illustrates the reasoning faithfulness of different methods on the folio dataset. It categorizes answers into faithful, unfaithful, and false based on the correctness and logical validity of the reasoning process. The COT method shows 6% of correct answers resulted from flawed reasoning. SymbCoT without a verifier reduces this to 2%, while SymbCoT with a verifier eliminates unfaithful reasoning entirely, demonstrating the effectiveness of the verifier in ensuring credible, symbolic-based reasoning. Figure 8 illustrates the performance improvement when upgrading from GPT 3.5 to GPT-4 using our method. The most significant boost observed is a 24.3% increase in performance. This underscores the synergy between our approach and more advanced models. In contrast, methods like Logic LM, which rely on external rule-based solvers, exhibit the least improvements with stronger models due to their dependence on LLMs for translation rather than reasoning. Thus, although translation quality may improve, reasoning capabilities remain unchanged as it is capped by external solvers. Our fully LLM-based method shows significant improvements compared to external solver-based approaches as model capabilities increase, indicating a promising advancement path in line with LLM's evolution. The Symbolic Chain-of-Thought (SymbCoT) framework innovatively integrates symbolic expressions and logical rules with chain-of-thought prompting to significantly improve the logical reasoning abilities of large language models, LLMs. Specifically, SymbCoT translates natural language context into symbolic formats and derives step-by-step plans using symbolic logical rules, followed by a verifier to check the reasoning chain. Experimental results on 5 standard benchmarks, using both first-order logic and constraint optimization symbolic expressions, demonstrate that SymbCoT strikingly enhances the performance of vanilla chain-of-thought on logical reasoning tasks. However, the framework has some limitations. It currently evaluates only 2 symbolic structures, and the implementation involves considerable financial costs due to the extended reasoning chains and increased token generation. Despite these challenges, the work adheres to ethical guidelines, emphasizing transparency, fairness, and responsible AI development. The broader impact of SymbCoT, aimed at improving logical reasoning in LLMs, has the potential to positively contribute to various fields, including natural language processing and automated reasoning. Thank you for watching.